Good afternoon, everyone. I say thank you for joining this my course. The course is a series. It's going to take 4 days. Today is day 1, so today is going to run for 2 hours, and tomorrow will come the same time of the Thursday. So, let me quickly. So, the course is about, the topic is on our screen. I will be speaking on Hamilton Ricci flow and Li-Yau Differential Harnack Inequality. Okay, so this course, well, is in a differentiable manifold. Some people say differential geometry, Riemannian geometry. It's in the intersection of all these. And my talk, well, it's gentle introduction to the course. It's gentle introduction to the course. Very gentle introduction to the course. We are going to see what the Ricci flow. We will feel what the Ricci flow is all about. Then we will see some analytical tools which are used to study Ricci flow. Then we'll do some computation. Yeah. Please let me work on my slide. Okay. So in this course, I will, as I said, I will speak on give some background to the course. Of course, for us to study Ricci flow, well, as an equation of Riemannian metric, we need to have some information about basic information about Riemannian geometry, because we'll be mentioning some of those stuff. So we'll talk about that, and in fact, we will take our time, though we will not go to detail, we will not do a lot of computation, but we will mention those things that are basic, especially those that are relevant to this course. We will mention them, then we'll go to Ricci flow, then we'll see several examples, and that is what we're going to do today. Let me give this as introduction. Ricci flow, okay? Ricci flow was introduced in 1982 by Richard Hamilton, in 1982. And informally, we can see it as just a process. Ricci flow is a process of deforming any given Riemannian metric. Now we call it a background matrix. So if you have a given background matrix and you flow it, then you want to get a canonical form. Yeah, you want to improve it. And what we mean by this canonical form is that you want to get a metric with constant curvature. Okay. This equation is captured as a nonlinear partial differential equation for the Riemannian metric, and it behaves in some sense like a diffusion of it, or the one we call it equation on the Riemannian manifold. This Ricci flow has been a powerful tool in geometry, in topology, even in mathematical physics. It has helped to resolve so many problems in geometry, in topology, most especially this long-standing Poincare conjecture, which has resisted so many solutions for over time before the introduction of this Ricci flow. And the basic of this Ricci flow, combined with some analytical tool from Perelman, they were able to solve Thurston geometrization conjecture, which has Poincare conjecture as its corollary. Now, this what we have in blue color here on this screen. So it's a Ricci flow equation. Okay, so Ricci flow equation, and we can see it this way. This is just introduction anyway, we will still see it. So we have this as a metric parameterized by T. Okay, I will explain all this, but this is just a formal way just to introduce it. I've said informally, it's a process of deforming this metric. This is a metric G, and we'll write this as an evolution with respect to time, that is partial T, to be negative of 2. Then this is Ricci curvature tensor of this metric GT. So this equation, yes, it's a Ricci flow equation. If you look at this one, Ricci curvature tensor can be expressed in form of a Laplacian, okay, with some other lower order term, so that this will look like you have something of this nature equals to, maybe let's say, let me just put Laplacian of G plus some lower order term. So this one look like our usual heat equation. Let's say U is a function on a manifold, and you can have something of this. Okay, we are familiar with this. So this behaves what you expect U to look like in a particular time, then we expect such for G in a particular time. Now, what we are going to discuss, as I said, we are going to keep our discussion as simple as possible, okay? Because we, even if you don't have any background in Riemannian geometry or in PDE, then that is not a problem. We just keep it simple. We are going to see examples. Everything that we need from Riemannian geometry, we mention it in the introductory parts. Okay, well, like I said here, the factor 2 that we have here is not very important, so we don't need to be worried about it. It is, you are going to see the reason why we don't need to worry about this maybe later, because by the time you write this Ricci curvature is going to be in form of maybe half of Laplacian. And these two, so it's just a scaling factor, so it doesn't really affect. But this negative sign is most important here to keep our flow forward in time, because by the time you write Ricci curvature tensor in terms of, it's going to be negative of Laplacian of G. Okay, so, and if this is not there, then it's going to be you want to solve backward, which we are not sure whether you can solve it backward at this stage. So this minus sign needs to be there. Okay, and we will discuss also later, maybe tomorrow, about the existence, okay, and uniqueness, at least short time existence of this this flow. We will see that this flow is not strongly parabolic. So it's so difficult to use the theory from our usual PDE to solve, because it is not strongly, it is weakly parabolic. And you know, the theory in the PDE is when you have evolution equation like this, which is parabolic, then we can use that. So in doing the existence, in 1982, okay, Hamilton used powerful theories from function analysis, Nash-Moshal inverse function theories to prove existence. Then later, shortly after that, in 1983, the talk used a way to just do a kind of conversion to make this flow strictly parabolic, so that we can now use a theory from a PDE to show existence of this, okay? So as I said, the aim of the course is just to introduce Ricci flow, the theory of Ricci flow, okay? Our focus will be on analytical aspects. And I said it's going to be very simple, okay? Analytical aspect. Precisely, we're going to discuss concrete example of Ricci flow, okay? Evolution of geometric quantity under Ricci flow. When the metric is flowing, other geometric quantities around the metric also flows. So we are going to see the way each of them involves like a curvature, volume, and some other things. Anyway, let me keep those terms because we have not introduced them. Then we will discuss short time existence, then uniqueness, convergence of Ricci flow, and we will look at some other analytical tools that is very important in the study of Ricci flow. Tools like the maximum principle, curvature derivative estimates, Li-Yau differential, and Hamilton matrix Harnack inequality. This is Harnack inequality, Li-Yau differential Harnack inequality, Hamilton Harnack inequality. We are going to see even Perelman Harnack inequality. Then we will introduce Perelman entropy and functional and some other terms. So this is what we are going to discuss in this in this course. Now, meanwhile, before we start proper introduction of Ricci flow, as I said, we need some background from Riemannian geometry. So we are going to start with that, and we will mention virtually everything that we need. Though we may not go into detail, but virtually everything that we need in the study of Ricci flow, we will just try to go around them and we'll mention them. And among those things that we mention, we will look at a smooth, manifold. Yes, what is manifold? Because we will be, all our work is on a smooth manifold. Then with what is tangent space? Okay, space of a tangent vectors. Then we need to know Riemannian metric. And then we need to know, well, we talk about length and distance as well. Length and distance, smooth manifold. And we also talk about connection. So, and of interest to us is Liouville connections. Then we talk about curvature tensors. Then, okay, I will mention a star metric is also very important because we are going to see a star metric as a fixed point solution to the Ricci flow. Okay, maybe let me just put this. So we will discuss all this. So maybe to start with, what is manifold? Okay. Yeah, maybe let me start with a topological manifold. I want to define a smooth manifold. Let's start with a topological manifold. I need this man. Okay. Yeah. Topological manifold, we talk about an n-dimensional topological manifold is a second countable Hausdorff topological space, which is locally homeomorphic to some open subset of n Euclidean space. So by that, we say, okay, maybe let M, you see that, let M be a topological space if M is a topological space, then we say that a topological manifold, we say that a topological manifold of n dimension okay, let me put that way. Anyway, don't let me. We say that M is a topological manifold of n dimension if it has these properties. One, if M is Hausdorff. M is a Hausdorff space. What do we mean by this? We mean that for every pair of points, if you have pair of distinct points, let's say distinct point PQ from M, and there are distinct joint open sets, say UV, distinct, they are distinct and they are disjoint, then such that you have P in U, and then you have Q in V. So these are open subset of M. So you have them and you have this point, then you say M is Hausdorff. Then as well, M is second countable. This is a background from a topology. By this, we say that there exists a countable basis for the topology of M. You have a countable basis for the topology that defines this M. And thirdly, we say M is locally homeomorphic. Okay, I don't want to mention that Marina. M is locally Euclidean. Of dimension N. Okay, so what do we mean by this? To say M is locally homomorphic to dimension N, we mean that each point of this topological space has a neighborhood that is homomorphic to some open subset of Euclidean space. And then say, let me give up this. Okay. To make it easy, let me just give us a kind of torus here. These are manifold, topological space now. Take M to be a topological space. And let's say we have an Euclidean space. I give a torus in dimension 2 to make it easier. So let's say this is R2. Say you have X, you have well, and Y, this direction. Then you have this, there's a point. You have a point P here. You have a neighborhood. Let's say this is U. Okay, that's it's U. Then there's an homomorphism which defines this and give an open subset of this here. You have these points. So this is the point that you're talking about. So the point P is appearing here. So by this, this is a map. This map is the homomorphism. Okay, so, and give us this, and this is phi. Okay, I will put P just to show that the neighborhood of P. Okay, so this is phi of P, phi U of P, which is just a subset of this R2. So you have this. This so opposites together with the map is what is called a chart. So, and what you are saying here is that you can pick another point, even you can have overlapping charts. You can have another point, then you have neighborhood of that, then there will be an homomorphism that take it to an open subset of Rn. So this is a topological manifold. You have this manifold taking an open subset of this to this here. So the idea behind this is that you have to cover this topological space with as many charts as possible, which we're going to see. What I said, like the second, okay, I have the second picture. I don't know whether I should, let me try to draw that again. Okay, I will use this. Let's say you have another point Q, and this is Q. Then you have neighborhood of this as Q. Then so you have point Q. So there's another morphism here. I'll call it phi of Q, taking U of Q. So this one is phi of Q, taking U of Q now. This also is an open subset. Okay, if you have this here. So this is you can have as many as of many charts, you can create as many. And these charts, you have collection of them is what is called an atlas. You can have collection of all these, then you have an atlas. That is, if you have finite union, maybe let's say phi of this is U alpha, okay? This is alpha, where alpha is from a finite set, then all this one give M. Then we say M is a topological space. So this is very, very important. So in what we have discussed here, we have said some things that the third property, I think, seen on the board. The third property I mentioned here, okay, we have said that there's an open subset U from M1, that's an open subset U from M, okay, containing P. This subset containing P of M. Then we have said that an open subset of Rn, I will say U of this from Rn. Then we have said there's an homomorphism of U, okay, which is this. That is by, okay, in Rn. So we have mentioned this. Now, this is a topological space. Let's see a topological manifold. There is something here which is called transition map. This homomorphism as a bijective map, okay, with inverse. Then, if you have an overlapping charts, let's say, okay, let me give you, okay, I will draw another one to make the point I want to make here. I want to define a smooth map. Okay, I talk about collection of a chart, which is an atlas. Now let's say we have so yeah. There's a point here at the intersection, and it's covered. This point here, let me just say P, which is in the manifold M, okay? Then we have this point here that contain P here. Okay. Then there is U, P, Q here. Okay, I use this as P. Let me say we have X here. Maybe that's better. Y here. This is UX. This is UY. Okay. So you have morphism to this place so that this is a phi of x of u of x. Okay. Let me put this one to face this side so that we have. Okay. So this P here, this one P here. So what you have here is another morphism, and you have phi y taking u of y. Okay. So you have now this is overlapping chart. And of course, you can have as many as that to cover the whole manifold as I wrote the other time. Okay, where did I write that? Okay. So yeah, if you look at this map, you can move, this one comes here, this comes here, then there's a map from here to here. Okay, I call that map for x, y. This here, this portion, it is phi x of ux intersects y. This portion that I shaded here, okay, that is phi y, that is u x uy. So if from here, this can move, we want to move here now. This map, phi xy, that is the composition of this and the inverse of this. You move from here, is as you move from here, you come here. So this is the inverse of phi x. You have the inverse. So this map it is phi y composition phi x inverse. And what does that take? That one take this set, okay, take point from here to this one. You can also come from this one. So what you have here, it is what is called transition map. So if you look at what I put at this on the screen, well, this the notation here is different. Okay. If you now say, if you have this chart and you have this transition map, if the transition map is C1, then you say M is differentiable. If transition map is C infinity, this would be C infinity. Okay. If it's C infinity, then you say M is smooth. It's not C1. Okay. Meaning that Atlas presents the smooth structure on topological manifold. So, and with this, we build what a smooth manifold is all about. And in this course, we'll be dealing with smooth manifold. It's going to be smooth manifold. Of course, we are going to deal with Riemannian manifold. We are still going to see what a Riemannian metric is. So by the time you had Riemannian metrics together with a smooth manifold, then you have a Riemannian manifold. Okay. So let's move to the next slide. So, please. Let's move my slide. Okay, thank you. Another concept that we need, now that we have established what, what we have just given here is not detailed about topological manifold and the Riemannian manifold, especially there are a lot of things that need to be said about charts and the transition map. to see the topology on the manifold and so on and so forth, but just to let us have a feel of what we will be dealing with. So it's not going to be, anytime we mention manifold, it is not going to be strange. Then we know that, yeah, we are talking about a set, a topological set. And what make that a topological set? Oh, to become a smooth manifold. Then later you will see metric. Then before we mention metric, another important thing that we need to mention here is tangent space, okay? Tangent space. Well, tangents, let's start with the tangent vector. Tangent vector to a smooth manifold M at a point P is a linear map, linear in R, a linear map X. We take X to be a tangent vector. Maybe let me give us, okay. Okay, if you look at the picture on the screen here, let me just give us that again. So let's say you have a point P here. Then the tangent space is what you have along this is a plane, okay, that contain here. Suppose on this, let's say you have a smooth curve running these points. Sorry, the picture is not good enough for me. Okay, let's say this is point P. And here you have tangent vector to this curve. Okay, this is a tangent curve going this direction. And this is the plane that contains all the tangent vectors you can have along all the points. And that plane is called the tangent space, which is more or less Euclidean. So the tangent space is a way of making points look locally like Euclidean, so that you can have a derivation in form of the vector in that plane, and you are able to work locally. Then, the set of all eigenvectors to n-dimensional manifold M at P forms what is called n-dimensional vector space. Okay, so which means a vector space, look, is of finite dimension and is isomorphic to Euclidean space Rn. Just I've mentioned. And locally, vectors consist of partial differential operators. So you can have, if you have a vector X along this line, okay, locally, it's look like what you have here. So you have at xp, so that is you have x, I, you have partial x, I, okay, here. So this is what a vector. And the chart that we tried to draw the other time gives what we have in local coordinates. Because if you come to this place, you can see the local coordinate. This is 2 dimension. I didn't mention that. Maybe let me come here. Say this point here. Okay, let's say this is x1, and this is maybe x2. So this point give local coordinate for P that you pick here. So this gives a local coordinate for P, 2 of P. So you have such. So in the n-dimensional, you have this n component. So this partial derivative, it is derivative in the direction of xi, in the direction of xi. So if it is x, you have I running from 1 to n, running from 1 to n, the dimension of the tangent plane. And the tangent plane is locally Euclidean. Okay, let's just move on. Then what is vector field? A vector field on a manifold M is a smoothly varying choice of tangent vector at each point P. Okay, suppose you have 2 vectors, x and y, from the tangent space, okay, the tangent vector at point P, two tangent vector at point P. You have two tangent vectors at P as X and Y, written as what I've just given. Okay, I just mentioned that you have the vector xi written like this and the cofactor like this. Okay, then you have Lie brackets written in this form. Okay, this Lie brackets written in this form. X is expressed this way, so you have this linear form. Then, okay, in abbreviation, as we move on, if I say partial I, then I want to mean the partial derivative with respect to xi. Okay, and we have not mentioned that, but we'll say that this nabla I is going to be a covariant derivative in the direction of this partial differential operator, this vector. Okay, so an inner product on a vector space allows us to define length of vectors and angles between them. So when you have that, it gives us opportunity to define length of vectors, you know, just in the form of equilibrium. Then you can see the angle between them as if you are in equilibrium space. Then the Riemannian matrix bring this structure to tangent space of a manifold. We have not mentioned, we still mention Riemannian code. Okay. Okay, let's just move on because we have a lot of this thing to mention. Now, a Riemannian metric. A Riemannian metric on the smooth manifold M. We have a smooth manifold M now, okay, and you want to put a Riemannian metric on it. A Riemannian metric is going to be a smoothly varying inner product on the tangent space at each point of M. It's an inner product on the tangent space. The tangent space now, you have X, you have vectors here, then you want to have the inner product of these vectors here in a smooth way. That's what a Riemannian matrix is. And if G is a Riemannian metric on M, these are some of the things that we should know. G is a tensor field. That is a section of the bundles that I denote as this. Okay. Well, I didn't mention this is a cotangent bundle that is I denote as this, where Tm is denoted as a tangent bundle. It's in the previous slide. So if you have G, okay, it's okay, it's a section of this, it's a section here, meaning that G is symmetric, G is positive definite at this point. By symmetric, let me just give us the this one so that we can speak. Okay, G at P, okay, taking X, Y. So by symmetry, okay, the definition, meaning this one as a symmetric space is like, I mean, inner product, I can have it as this. Why this inner is with respect to metric G. Let me give, yeah, at point P. So by symmetry, GP is equals GP of YX. Okay. By positive definite, well, let me put greater equals to is to 0, okay, at each point P. So this is what we have there. Then if you have this structure, this Riemannian metric with those properties, let me see what I have with the next slides. Okay, before I mention what is written. Then you put this inner product on the smooth manifold that we have defined, which I write it as G. This pair is called Riemannian manifold. You have a smooth manifold, then you put Riemannian matrix. The pair is Riemannian manifold. So we are going to be talking about Riemannian manifold. All our discussion is on Riemannian manifold. Then locally, that is in the local coordinates xi. Okay, if you can see the local coordinate xi, then G is written this way. G, we write it in component form, Gij. This symmetry means you say Gij is also Gji, okay? And you can see what you have here, or you can write it just as this quantity, okay? Here, this is a tensor product. Then G's provide a bilinear function on the tangent plane. Okay, the metric inverse of Gij is also denoted. The inverse of Gij here, if you have Gij, the inverse is going to be G. I will denote it as this. This is the inverse of this metric. Okay, and you can example of that. Rn itself is a Riemannian manifold. Rn is a topological space. Then it's a smooth manifold because all those properties that we mentioned the other time is on Rn. Then you can have this the usual Euclidean matrix. The usual Euclidean matrix on Rn forms the direct data forms a Riemannian manifold. Okay, and another example, you can have a product metric. Okay, you can have a product metric. If you have M1, G1, you have M2, G2, there are two Riemannian manifolds. Okay, then by natural identifications, you have the tangent space of the product. Okay, because it's a product now, just like a Cartesian product, then every point here has the two components, P1 and P2. Okay, so say P1, P now, because the product of two. So the tangent space at that point, P1, P2, okay, of the product manifold gives, okay, direct sum of this and this. So, and you have a canonical Riemannian matrix G, which is going to be G1 plus G2 on M1 cross M2. So you can see this is the way it's defined. Let's say you have vectors U1, U2 from a tangent space at P1 of M1, P1, M1. This is tangent space at point P1 on M1. Then you have these two tangent vector U1, U2. Then on the tangent space at point P2 on M2, you have these two tangent vectors. Let me. Okay, so you have the product example I'm giving here. Let me write it again. I give a product metric. You see, you have M1, G1. Okay, this is Riemannian manifold 1, and you have the second Riemannian manifold M2, G2. Okay. Then you can define tangent space. You pick P1 from M1. Another point, on M2, you have this point. Then you can define target space, because if this product, you can define target space of P1 of this M1 plus M2. So what we are now saying is that if you have this U1, another U2 as vectors, okay, in this tangent space, let's say I have V1, V2 in this tangent space. Okay. Then metric G on this product is given so the metric here can be written as this G, okay, P1, P2 of U1 plus U2, V1 plus V2 equals G, okay, P1, this is metric one, first one, in this direction of U1, U2 plus GP2 of V1, V2. So where you have that. So that is what that example. Okay. The next we want to mention here is the tangent, the length at distance. Okay. Let's say give you have a piecewise smooth curve from this interval AB, okay, to M, and it's defined. We are using Riemannian metric now to define. You have a Riemannian manifold M, and then you have an interval from A to B. Then you have a curve on that interval, which is piecewise smooth. Well, piecewise is okay. I mean, piecewise smoothness is okay. Then the length, which we'll call the length of that curve in M, L. This is the curve. Is defined as this integral AB. And you have G at this point of this curve. Okay. See, T is in the interval AB. So this is a derivative of this curve, vector curve, is to the power half dt. Okay, so I defined what this. So this is what you have as the definition of that curve, and you can just look at this. Say this is an interval. Well, A, B, and let's say this is your manifold M. Okay, let's say you have I'm taking this curve to this place. So where you have a point P and you have a point Q, such that the gamma of A is P and gamma of P is Q. So you have this here, and this, apart from P to Q, you can have as many. So this curve and the length of the curve that we define here, can allow us to define distance, yes, from 2 points on the manifold. You can have as many, you can move from here to here in different ways. You can move like this, can be like this. So you can have as many ways to get here. It is not straight line, except this is a flat, yeah, except this is a flat manifold that distance between point P to Q can be a straight line, but in this case, it's not going to be a straight line. So you can have that. Okay, please let me. Excuse me. Okay. Excuse me, please. So with this, we can do a kind of, oh, sorry. I should have, well, it's okay. So this allows us to define distance, and we can have, if you define the distance, it is easy, it is not difficult to see that distance between P and Q that we define, okay, let me mention it, lay emphasis on it. The distance between, okay, sorry, the one I just, P, Q. So this is gamma of A equals to P, gamma of B equals to Q. So here you have as many lines as possible. Okay, so distance between P and Q on this manifold is defined as infimum, okay, of the distance. Okay, such that you have those conditions. And from here, it is easy to see maybe let me say 1, that this one is greater or equal to 0. Okay, then you can also see that so this is a symmetric property. You can flip from P to Q, you can come back from Q to P. So you have that. And you can also see equivalence of triangle inequality, that dpq is less or equals to RQ. So you have this, okay? Most importantly, look at this, you can also find that dpq equal to 0 here implies that P equals to Q. So you do this property, then if you put this distance that we define now on a manifold, then this manifold becomes a metric space. The manifold becomes a metric space. Okay, so and you can use this one to prove that, oh, Riemannian manifold is a metric space. Of course, because you can use metrics to define distance between 2 points on the manifold. And we have some important theorems here. Okay, if M is a Riemannian manifold with metric G, then M is a metric space with distance function, which we've just explained, and we can prove that proposition. Then there's this another important theorem. Yeah. Okay. Which says, okay, suppose M is a connected and smooth Riemannian manifold if M together with this distance is a complete metric space. Of course, we can prove that completeness with this metric, just like in the case of Riemannian manifold. You try to build the Cauchy sequence, and you see the convergence of those within the set, the manifold. So if you have M together with D as a complete metric space, then every closed and bounded set of M is compact. 2, for any two given point PQ, there is a unit speed C, yes, from that interval to M, okay, from P to Q, such that D of this distance is just the Euclidean norm S minus T for LST here, which defines the infimum. And in fact, this in line with, okay, let me mention this one before I mention that important theorem of Reynolds theorem. If MD is complete, this is a corollary to this theorem. If M, to these two proposition and this theorem, if M is complete, then it is compact. If and only if it has a finite diameter. What do we mean by diameter? Diameter is a supremum of all these distance I put here. Distance P from Q, the supremum of all them is what is called diameter of manifold, because we will still mention diameter, and that's what you have here. So if you have diameter, which I just write as the of M together with the distance function with respect to metric G, okay, is a supremum of all these distance. The distance now is with respect to G from P to Q, such that you have this PQ from M. So that. And you Reynolds theorem prove equivalence of certain statements, saying that, okay, every, like you have here, every bounded, let me write it down. Okay. So if you have M, let it be a connected, smooth, one. The following statements are equivalent. The following statements every closed and bounded subset of M is compact. MD, this is a complete metric space. Then M is geodesically complete. Okay, well, I've not mentioned geodesic, but let's just keep, which is geodesic complete is equivalent to the second statement that I have here. So what I'm trying to do here is that I want us to have a good feel about this manifold, Riemannian manifold, so that whatever background that we have, okay, as a topologist or as even the elementary knowledge of set, we will see that Riemannian manifold is something that we are familiar with from a set a topological space, topological manifold. Then you see the property. You can have distance. Yes, the distance is not Euclidean. It depends on the Riemannian metric that we have on the board. But at the same time, you can still have make it a metric space. You can prove completeness in terms of metric space, and you can see the equivalence. If it's a complete metric space, then every closed and bounded subset you have there is compact, and then you can define geodesic, and you see that once it's complete as metric space, it's also complete as a geodesic space. So I'm just giving us this background so that we are familiar. Whatever background we have, then we know that it's a Riemannian manifold is what we know. Okay. Then another important thing that we need in this setting. Another thing that we need in this setting is a diffeomorphism and Lie derivative. I need to speed up now. A one-parameter group of the diffeomorphism of a manifold M is a smooth map defined as what I have here. Okay, you have 5 from M. Okay, you know what a diffeomorphism, which is the diffeomorphism is a bijective smooth map. Okay, yes, the inverse is also smooth. It's also it's also smooth. Then you define it between topological spaces. Now we have a diffeomorphism between M and M now. But this diffeomorphism is parameterized by T, so that you are having this line here. Then if you have phi T as diffeomorphism and you have phi naught as this identity, then you have this group structure here. Then this is a one parameter group of diffeomorphism. So we need that. That is, if you have any P here, then you have the flow of that diffeomorphism by the vector field at that point. Okay, so by that we say phi T is the flow generated by the vector field X. Good. So then this is just definition and properties of Lie derivative. Okay, of Lie derivative that we have here. For a scalar function, if you have this, you have the derivative at t equal to 0 of this pullback of vector field. It is the Lie derivative of f in the direction of x. So the Lie derivative of that f, maybe as a tensor now, in the direction of x is defined as what you have. And particularly, if you have a scalar function, okay, the point bullet 1 here, the Lie derivative of f is defined as that. Then for any vector field y, you have the Lie derivative as this. Also, and you have the other two properties. Then another important thing is connection. Okay, so connection you have defined as this. Okay, a covariant derivative is defined on the board do he over M, which is a map with this property. Okay, yeah. So what we say here is that if you have a connection, okay, let me speed up. If you have this connection, with respect to this vector field of this function here, so this is the covariant derivative of this in the direction of x. Covariance of this function in the direction of vector field x. So it's denoted as this. And you have this property. It is infinitely linear in x. So you have this, and it is R linear, okay, in this form. And this one satisfies the product rule here. So, okay. The most important to us here is the Liouville connection. So this is Liouville connection. Yes, if you have Riemannian manifold, there's a theorem here. We call it fundamental theorem. of Riemannian geometry. So which says if you have a Riemannian manifold, then you have a unique connection here, which is called Liouville connection with these two properties, this property here, that is the connection preserves metrics, okay? We call it metric, Riemannian metric compatible. And by that, you have this property here, which is equivalent to say that covariant derivative of G's is 0. So that's that. And it's also torsion free. That is for any vector of x and y, okay, you have this, that is the Lie derivative, the Lie bracket becomes this. So this is what you have, meaning that the torsion is 0. Torsion itself is defined, the torsion between x and y is defined as a gradient of xy minus of yx minus the Lie bracket of xy. So when you have this guy equal to 0, then you have this equals to this. So that's what you have here. And you have this lemma. Okay, we need to move on. Then another important thing that we need is a Christopher symbol. These are just Christopher symbols. Okay, these are the coefficient of the connection of Liouville connections. So in local coordinate, it's written this way. Okay, yeah. So these are Christopher symbols. Yeah. So that is in local coordinates. You have it like this, and you can express it as this 1/2, okay, JK L GJL plus GIAL L minus. Okay, you have L GIJ. So this is what you have in local coordinates. When this is Asian, let me just, we can move on. This is Asian and Laplacian. Another important tool that we will use is a differential operator. So at least because you say Ricci flow is a second order differential operator, so we need differential operator. Then we mentioned this covariant derivative is a differential operator of first order. Then of second order, we can talk about Asian. Suppose you have a tensor, you can find the second covariant derivative of that tensor like this. That is Asian of T. You can define rough Laplacian on that. When you have the trace of Asian, then you have the Laplacian on that T. It's locally written as this. Also, if you have some smooth functions, you can define the Asian of that smooth function, and then you can define Laplacian of that function as well. That is called Laplacian-Beltrami operator, Laplace-Beltrami operator. So you have that as well, and we will be referring to that later as well. So this is a theorem. We will use this theorem also, this lemma as well, very well, that you have Lie derivative of metric Gij with respect to in the direction of gradient. Okay, let me just write. Yeah. Okay. So now suppose you have this x, and let's say you have this x, okay, is given as this. I defined that earlier on. So the theorem says that you can have Lie derivative now. Okay, can I write it properly? Lie derivative of this metric is in the direction of x. Okay, that's what we are. We have the sorry, please. Yes, I'm sorry. Okay, we defined the derivative here already for f, the derivative of that. Then here we are. Okay. Sorry. This is the lemma we are talking about. I just want to take a specific example of this x, if x is given as a gradient of a function. So I can have this lead derivative of g in the direction of this vector, okay? And the theorem says that this is just the two Hessian of function f. F is a function, is a smooth function on M. So that can be proved. Then curvature tensors is also important here. In fact, they are very, very important. We are going to do with them because we will still come across them, and we will talk about them in detail. Maybe I should just browse them now. So the curvature tensor is denoted as this R, okay? And local coordinates is written as this. It's a 1-3 tensor, so where you have this L up and you have IJK lower components. So it's written as this, okay? So YR is written as this. So accompanied with this tensor, then you can have this 0-4 tensor like this. So these are X, Y, Z, W. These are vectors. Okay, this curvature operator takes this tensor and these vectors, and it's written as this. So you have G here, okay, where it takes this, yeah. Then for all vector field X, Y, Z in this section, they are section of this tangent. Then you can express it as what the expression that we have here. Can express this function where you have this Rijk, that is, you can raise index, you can lower index using this metric. That is what we do here. We are going to use this in some computation, especially when we want to see the behavior of metrics. Behavior of curvatures under Ricci flow. Okay. Then this is a lemma. We just keep that here. And then there's properties of symmetric tensor. Okay, it's anti-symmetric in two variables. You can see this symmetric identity. The line here. Okay. Then those things I wrote in red, these are properties. Okay, of curvature tensor, symmetric, anti-symmetric in the first two variables, also anti-symmetric in the last two variables. So when you change that, it's going to be, and that's what you have here. It's symmetric in the first variable, that is this. Symmetric in the second variable, that is this. Okay, then this is what is called first Bjerke identity. So you have this sum equal to 0, and this is second Bjerke identity. So they are very, very important that we will come across. Okay, then another important thing about this curvature, to get information about this curvature, you can trace, okay, this curvature, we can trace it, do the tracing on this, then we have a Ricci curvature tensor. Okay, so Ricci curvature tensor is a 0-2 tensor. So, and in component form is written as this. So here you have tracing out the decay. Yeah, so you have Rij, and it's written like this. Then you can do tracing on the Ricci tensor as well. Then you have a scalar curvature. Okay, so there's this lemma, which we just want to sketch through. Okay. Can see that this lemma, if this is divider connection, you know, it's metric compatible, of course. Then we have these these two items here. Gradient of this or divergence of this Ricci tensor gives this. Then the second order, yeah, okay, maybe I should have written this one. This quantity here, KL, it is, I want to make this. Okay, it can be expressed as this. Okay, and you can have contracted second Bjerke identity as this contracted second Bjerke identity. If you do the tracing on the first second Bjerke identity, you have this, which says the divergence of Ricci tensor is the half of gradient of a scalar curvature. The divergence of a Ricci tensor is this. So we will make use of all this. Okay, this is as time metric. This is also very, very important. As time metric, we say Riemannian metric is as time, or you say Riemannian manifold is as time if the Ricci tensor is a scalar multiple of the metric. You can write it like this: the Ricci tensor of the metric is a scalar multiple, then you call it as time. Okay, and from this quantity here, you can get this quantity. Do tracing this. This is the equation. Rij equals to lambda Gij. This lambda is a constant from R. Okay, so this says when you have this condition, it says the metric is as time, or you say the manifold is as time. Then from here, if you do the tracing from here, you trace this. I say you trace this, you get a scalar coefficient of this. Then you trace this, the tracing of Gij. You can do the tracing using Gij, the inverse metric, to do the tracing on this quantity. So you do that, you get the scalar quantity here, and you do it here, you have on this one is n lambda. Okay, and by that you can get lambda to be 1 over n r. So as that condition give us this. If you put this guy inside here, then as that condition give us this. And once you have this, then that is what is called as type condition. Okay, and you can define this quantity here, like this definition. So that tensor that is defined as this is called as time tensor. Okay, so when you have this, then we say the metric, okay, the Riemannian manifold as time tensor. Okay, so you can do this. This one say, okay, on as time metric or the manifold of dimension n greater than 0 as a constant curvature, and this is just the proof in a short way. Okay, do the divergence. This is start with as time tensor, do the divergence on both sides. This is divergence of this is divergence of this, and when you do that, this is what you have for n greater than 0. Shows that this quantity is 0, meaning that gradient of R is 0. And when gradient of R is 0, gradient of a quantity is 0, it means that quantity is constant. So that's what we have there. So I think I need to rush because we still want to do some other parts. Yeah. So this is basic, and what we have just discussed, is like a whole lot of book, you know, many things, and that's why we have to just mention them because we need them. We have these references that we can use if we want to study or to want to see detail of most of those things that we just mentioned. This book is book by Lee. Yeah. Then this book, I like these books. They are very good. They have detail of those things that we have discussed. Then, so with this background, then we should be able to give us definition of Ricci flow and do some stuff using Ricci flow. Okay, so that is the first part. And in the next 20-25 minutes that we have, we introduce Ricci flow. Okay. Let me take water. Without Ricci flow, we just have 2 minutes break. Okay. Welcome back. In the introduction, yes, I mentioned Ricci flow just as a process of the forming Riemannian matrix so as to get an improved form or a canonical form, that is to get a metric of a constant curvature. So I want to introduce it formally now. Yeah. Okay. So this is the equation that I mentioned it earlier on. This is the equation. So you want to run it as a process, then you want to start with a given metric, and that is an initial condition. So you have G at, let's say, time. Now take this time. Okay, yes, an abstract time. So at G at time t equal to 0, you have a prescribed, you have a given initial metric. Then you can run the Ricci flow. So which means you can prove this now become an equation now, initial value problem. Okay, so we are going to see in detail how this one can be written as a just a partial differential equation. It's a partial differential equation now, yeah, parabolic. What we want to see, okay, how parabolic it is. Okay, we'll say tomorrow, but let's discuss this and give some example to fill it. I mentioned it earlier on that factor 2 here is not very, very important to us here, but the negative sign ensures that the flow remains forward in time. Then I mentioned it earlier on also that this system is of weakly parabolic, which we are going to show. We do that. Okay. Then I said that it was introduced by Richard Hamilton in 1982, and it proved existence using implicit theorem from function analysis. But the talk also gives a short proof later without using those powerful skill, but a way to reconstruct this using the Devomorphism invariance of Ricci curvature, which makes it to be not actually parabolic, not to be strongly parabolic, and do a kind of transformation to get the solution of this. So that is what you call the talk Ricci flow. We'll mention that, but that's tomorrow. But we will also prove the short time existence of that. Then this equation now, the solution can run to singularity. We'll see example now. Okay. Let's give an example of Ricci flow. Let's give an example of Ricci flow. Okay. I want to start with our time metric. I think that's where we stopped the other time. Example, let's start with our time metric. In the definition of our time metric, we said the Ricci curvature of the metric is a constant multiple of that metric. So where this is, okay. That example says, if you start Ricci flow on this, okay? If you start Ricci flow on this metric, say metric G naught, say you start Ricci flow with metric G naught, that says the Ricci flow in time t, at time t, will be 1 minus 2 lambda t G naught. That's what that example. Maybe we should just quickly see that and see that GT will represent this. Okay, maybe I quickly write. Let's say Ricci of G naught. We start with this. Okay. Now, suppose you have GT, maybe You parameterize this G naught with this, and this GT solves the Ricci flow. Solve the Ricci flow equation. Okay. If you have this, then let's have the Ricci flow equations. Differentiate this. What do you have? You have, with respect to time, this G naught is the initial metric. T is equal to 0. Is cost. You start with that not with respect to time. It's like a constant. It's only the parameter that you have here to rescale this that depends on T. So by that, you have alpha prime of T. That is first the derivative of alpha with respect to time. Okay, this quantity G. Then from definition of Ricci, this one should be -2 Ricci of GT. That is definition of Ricci flow. Ricci flow says this is Ricci flow. That's definition. So you have this. Then by the scale invariance of a Ricci curvature tensor, then you have the Ricci of this quantity here. That is Ricci of this GT that we are going to use here. GT is this, which is alpha T of G naught. Because of the scale invariance of that is same thing as Ricci of G naught. Okay, so this, what you have here, combine them together, you have 2 lambda G naught. Okay, this is lambda G naught minus 2 multiplied by this, give you -2 Ricci of G naught. This one you have started with. And it is here, which is the same thing as this, -2 Ricci alpha T of G naught, which is equal to -2 Ricci of GT, according to what you have here, and this, which is equal to this. So by this, you just have yes, I think yes. Yes, you just have this from here. This -2 here, this and here. So you have this. And this one become ordinary differential equation. Can we have initial condition at T equal to 0? From here, if this is 0, this is G naught, this is alpha naught, this is G naught, then alpha naught is equals to 1. So you have this together with alpha naught equals to 1. So you can solve this. So when you solve this differential equation, you have your alpha of T to be 1 minus 2 lambda T. So solving that, and you take that condition, you input back into this where we start from. So you have this condition. Okay. And the meaning of this is that T, if you have this, it means that this GT, okay, degenerates at the point T equals to 1 over 2 lambda. This thing degenerates. Okay. The Ricci flow becomes singular at this point. And there are 3 possible things that you can have here. If T is positive, if T is negative, if T is 0. In fact, from here, T positive here means you are talking about a manifold with positive Ricci curvature. T negative means you are talking about manifold of negative Ricci curvature. And if lambda is 0, then you are talking about a manifold with a flat metric. So, and here, The Ricci flow here corresponds to what you call a shrinking, steady, and expanding soliton, depending on the values of this lambda. So here, if lambda, maybe I should just, let's give us some pictures to see if lambda is greater than 0. I think I have some pictures here. Okay. You can see if lambda is greater than 0, the Ricci flow contracts G. Since the scale factor you have here is less than 1. Okay. So this contract, and if you have, let's say you have a sphere, let's give a sphere for example. We know a sphere has a curvature of 1, constant curvature of 1, okay, which is a lambda equals 1 here. Let's take lambda equals 1. So if you start with this initial matrix, then at time t, okay, here, this Ricci flow shrinks the sphere. It shrinks it, and it becomes shrinking. So until it changes. So at this point t, okay, equals to 1/2. Lambda, I take it as 1. So if this is the direction of the flow, at this point, this becomes singular. And what I mean here is that everything about manifold degenerates, the curvature, okay, the curvature is behaving in a way, the diameter is behaving another way, and you see this degenerate become a point. So this is what you call example of a shrinking solution. This is a shrinking round sphere. So that's what we just put here. For t positive, you have this kind of thing. Okay. So the diameter goes to 0, the curvature goes to infinity, and the manifold now collapsed. So it is not just only on sphere. Any manifold with positive curvature behaves that way. If you have a manifold with positive curvature, the Ricci flow, we try to make it round, to make it round, or become like a round sphere, and it degenerates to a point. Then, if lambda is negative, okay, if lambda is negative, okay, let's give the case lambda equal to 0. Then we say we have Ricci flat. Okay, that is the case. Have a torus. So in this case, lambda equal to 0 is synonymous with G being Ricci flat. Then G is independent of time, because if you have Ricci to be flat, then your equation becomes something like this. The Ricci that is here becomes 0. You have this. So this becomes independent of time, and it exists for all the time. Okay, it remains static. And that's what we call a stationary solution, or you call it a steady solution. Then for the expanding, if lambda is less than 0, the Ricci flow expands G, okay? And since the scale factor that we have there, 1 minus 2 lambda t will be greater than 1 for all t greater than 0. So you have the one of a negative curvature. This is a manifold with genus equals to 2 here, or maybe a double torus. It's an hyperbolic space with negative curvature. Okay, the curvature of this is going to be minus 1. In this case, it expands. Okay, it expands and invulate, because here the diameter is getting to infinity. Okay, the curvature is becoming small, and you have it this way, as you have on the board. So this is a Ricci flow on this. So this basic example. Another example is that you can have Ricci flow on a product. Ricci flow on a product manifold. Okay, if you have product of M, I, J, I, T, T, I, maybe let's take 2, I, is from 1 to 2. Then the Ricci flow preserve product structure. In fact, the component, let's give an example to see what I'm saying. Suppose I have a picture like that. Suppose you have, let's say you have S2 cross R. Okay, this is a cylinder. The Ricci flow on the equilibrium, we said is steady, it doesn't change. But on a sphere, which has positive curvature, the Ricci flow shrinks it. So if you have this product, just like a cylinder, then it gives you, this is what you call shrinking cylinder. You have a Ricci flow like this, okay? This is a cylinder. And when you start, then over time, the Ricci flow keeps this, but this one is becoming shrinking. Then it goes like that. The sphere is shrinking until it changes to a line, because this one becomes points. So this is a shrinking cylinder. You can see the Ricci flow is keeping its own properties on this sphere and on the equilibrium. So that is the example I have here, the shrinking cylinder. I have the picture here. So this is another example here, maybe double toroid T2 plus T2. Yes, each of them is evaluating. And then you can construct as many examples. You can even have two, okay, maybe product of S2 and S2, but one is smaller, radius of one is bigger than the other. You can see it's degenerating, but one will degenerate faster than the other. And so on and so forth. So the Ricci flow on a surface, well, on dimension 2. That's another example. If the dimension of the manifold is 2, the Ricci curvature can be expressed in terms of the Gaussian curvature. In dimension 2, the Ricci curvature is written as a product of the Gaussian curvature and the metric. Okay, so you have this, and the K is the Gaussian curvature of the surface. Then you can write the Ricci flow on two-dimensional manifold as this. Okay, so if you start with a metric with a Gaussian constant Gaussian curvature, let's say it is kappa, like what I did the other time, the flow is this, and you can easily show that the Ricci flow becomes this. Well, you may want to just justify that this quantity 2 kappa over minus 2 kappa, no, 2 kappa over 1 minus 2 kt is the actual value of Gaussian curvature. So you can do that. And this one shows, yeah, these 3 possible things. And look at this picture. If you have a 2-dimensional manifold, yes, the side, the parts with a positive Gaussian curvature tend to strings. The parts with a negative curvature tend to invulate. Okay, and that is what we have here. Okay, so you have that. So this one tells us that the sign of curvature greatly affects the behavior of Ricci flow. Yes, by the Ricci flow. So like in this Gaussian I've given, in fact, you can see this as well. If you have, I just use this to explain. Yes, just for us to view. Let me go back here so that you can see something here. If you have kappa equal to 0, then the Ricci flow doesn't change for all the time. For all the time, it's eternal. The solution is eternal from minus infinity to plus infinity. If kappa is greater than 0, then you have your time between minus infinity to 1/2 kappa. That's the time, the existence time for the flow. And the solution shrinks to a point as time approaches 1/2 kappa. Okay. Then if kappa is less than 0, the solution shrinks to a point. If t is coming back to 2 kappa, or you have the metric expanding as it goes to infinity. And that is what I try to illustrate here. About this provide a basic background to prove, to use Ricci flow to prove uniformization theorem. So, well, in most of these things, we just assume a priori the existence of solution. You know, we have not really dealt with solution, but we assume that, okay, G is a solution, then this is the behavior of what you have. Maybe let's check term. Okay. Yeah, we have mentioned this, and property of Ricci flow, okay, parabolic rescaling. Parabolic rescaling, if you rescale metric, okay, because Ricci flow has a scale invariance, just because Ricci curvature tensor, Ricci tensor is a scale invariance, the Ricci flow has scale invariance. Here, if GT is a solution of Ricci flow, then you scale G lambda in this form. This is also solution of Ricci flow. And you can show that just this. Okay. So it's just a simple computation. And then you see that this quantity, another is diffeomorphism invariance. Okay, we're supposed to, okay, let's just explain. The diffeomorphism invariance curvature, if phi is a diffeomorphism, okay, between M and M, you have manifold M, you have a manifold. Okay, maybe this is a metric here. And this metric, this is about, okay, it's M and M. Then, so you have this here. Then, if we do okay, a pullback. So the Ricci curvature of pullback of this metric, you pull this matrix back with this. Even if you do push forward of metric, yeah, the Ricci curvature of that quantity is this multiplied by this phi star, that is the push backward of using diffeomorphism multiplied by the Ricci curvature of the metric. So that is a diffeomorphism. So this vi here, okay, is a diffeomorphism generated by vector field, okay, and this says Ricci curvature tensor is diffeomorphism invariance, Ricci tensor. So if this is what I just explained here. Now, using this, if you now define G okay, and you know that this G is a Ricci flow, that it solves the Ricci flow equation. Then we can prove that this G is a solution of each equation. I mean, solution of Ricci flow equation. If this is a flow equation, that's what you have here. This is M. Okay, now we have GT of M here. This, you start Ricci flow with this. If you push this one backward here, then this GT here is of this, as I wrote here. Then this is Ricci flow. And this is the computation here. Okay. So meaning that Ricci flow is invariant under full diffeomorphism group. So maybe this is a convenient point to stop for today. So let me give us some references I have here. So I have these references. Okay. So I will stop here for today. Thank you.